Welcome back to my series on building an NES emulator. Last time we looked at assembly language, which is how commands are communicated to the CPU. Now that we know what the CPU needs to do, we can start designing our emulator. In case you're new, I'll provide a link to the first video in the series in the description for this video. Each time the CPU does one step of work, it is actually going to do each of the following. 1. Determine what instruction it is going to run. 2. Read or fetch that instruction. 3. Decode it, so it knows what to do. 4. Run that instruction. And 5. Repeat. Let's talk about each in more detail to remove any more mysteries in the CPU. When we looked at registers in the previous video, we saw that the CPU has a register called PC, or program counter. This holds the memory address where the next instruction starts. When running an instruction, it is assumed that the PC gets updated to point to this next instruction. So step 1 essentially means look at the program counter. For step 2, the CPU needs to read from memory. We saw that 6502 instructions use only the first byte to set the command through the opcode of the instruction. Some other bytes may follow for the input, but we can leave the rest for the decoding step. Next up, we actually have the decoding. This means turning some byte value into something meaningful for the rest of the program. There are technically 256 different values possible for that one byte. Does this mean our CPU emulator needs to handle 256 different instructions? Yes and no. While programs can technically use any value for the opcode, only some of these are actually documented or official instructions. On a real system, the other instructions will either freeze the system or perform some combination of documented instructions. Nearly all programs for the NES use only official instructions. So for now, we'll only care about these. We might revisit the others in the future. You can find a full table of these valid instructions in most 6502 programming manuals. I'll include a link to one in the description. You can see here that of the 256 possible values, only about half correspond to official instructions. You might also see that a lot of these use the same assembly language name. For example, these are both LDA instructions. This brings us to addressing modes. The designers of the 6502 instruction set realized that programmers might want to apply the same type of operation to different types of inputs. Sometimes the value you want to work on comes from a register, and sometimes it comes from memory. Rather than have two completely different instructions, it is represented as something like add plus memory or add plus register. These are called addressing modes, and the 6502 has quite a few. Rather than cover all of them here, I'll point out just a few. You can find more in the reference linked in the description. The first addressing mode we'll look at is immediate. Here, the value is encoded directly after the opcode and refers to the exact value of that byte. We actually saw this with the LDA example earlier. The pound sign signifies that this is an immediate. And when we look at the assembled machine code, we can see that the 20 is directly copied after the opcode. What if we remove the pound sign? Here, LDA $20. This single byte that follows is a 0-page address. This loads a value from memory at address 0020 and assembles to machine code A520. Since the 6502 does not have many built-in registers, it would otherwise be pretty clunky to constantly have to swap from registers to memory. Fortunately, the 6502 allows easy and efficient use of the first 256 locations in memory and calls this the 0 page. We saw that on this system, memory addresses are normally 16 bits or 2 bytes. If we actually assume one of those bytes is all zeros, we can represent a memory address using only 1 byte. This is how the 0 page works. 0 page addressing can be used to point to values from address 0000 to 00FF. Programmers typically put the most frequently used variables in memory in this range of addresses. When we were looking at the machine code for the earlier instructions, you may have noticed that they are very similar, A5 versus A9 for the opcode. Fortunately, this is not an accident, and is one other way that clever design has made the CPU easier to implement, both in the original hardware and for our emulator. The encoding typically uses some bits for the operation and some other bits for the addressing mode. This means that instead of implementing 128 completely different instructions, we can implement roughly 56 unique operations plus 13 addressing modes. Let's look at encoding in a bit more detail, and we can see how to make use of this clever design. If we take an 8-bit opcode and refer to bits in chunks, the CC bits tell us which instruction group this is. Each instruction group supports the same set of addressing modes. Group 1 with CC equals 01 is the most flexible mode and supports most addressing modes. Let's keep looking at Group 1. Within Group 1, the AAA bits tell us which operation it is. LDA is 5, or 0B101. Finally, the B bits are the addressing mode. 2, or 010, is immediate, and 1, or 001, is 0 page. So if we revisit the two instructions we saw earlier, first our LDA immediate, A9 in binary represented here, then we group the bits. We can see LDA is 5 as we expected, and the addressing mode is 2, which points to immediate. Likewise for the 0 page instruction, A5 in binary we have here, we group the bits. We see A points to LDA again, and B points to 0 page, just as we expected. Once we have the instruction decoded, we need to perform or execute the requested work. This should be easy, assuming you're using a high-level language. Implementing LDA in C, for example, would look something like this. Value will implement the addressing complexity we talked about earlier. Before we consider an instruction complete, we need to make sure that PC is updated to point to the next instruction. Addressing modes also help simplify this, since the length of an instruction depends only on the addressing mode. Immediate and 0 page will always be 1 byte, and there are some other addressing modes that use a full address, 2 bytes. Once we know the length of an instruction, the PC update rule is essentially, if the instruction didn't change PC on its own, we set PC to point to the old value of PC plus the length of this instruction we just executed. Otherwise, don't change PC. This second case accounts for branching, where the instruction's purpose is to set the CPU up to perform a different instruction. If the CPU also updated PC in this case, it would miss the target instruction. Now we have a pretty good outline for our CPU emulator. If you want to get started, you could use the table provided and the knowledge from this video to build most of the 6502 emulator. One thing we haven't yet addressed is the status register, which gets updated by most of the instructions as a sort of side effect. We'll take a look at the status register and one more exception to the PC update rule in the next video. That's all for now. See you on the next one.